Alright, in this video we're going to go over insertion sort. So let's first do a quick demo of what insertion sort looks like. So let's say that we want to sort these 5 numbers in ascending order. The way insertion sort works is that the sequence taken in blue is considered to be in sorted order, and the sequence that's in gray is considered no particular order. And the way insertion sort works is that you take the first element in gray and you insert it into the blue sequence, so making the blue sequence in sorted order. And the way you do that is that you just keep checking every element that it's next to and switching it if necessary. So 4 is right next to 7. If 4 is less than 7, then you swap it. And you keep doing that until it's less than the element on its right. You keep doing it until it's bigger than all the elements on the left, or until it's the first element. So in this case it stopped because it reached the front. So now the front's in sorted order and the gray sequence is still not in order. So then you take the next one in the gray, which is 2, and you insert it into the blue sequence, and now you need to sort the blue sequence. So you compare it to every element that it's next to. So since it is less than 7, it's going to swap, and because it's less than 4, it's going to swap. And now it's hit the front, so it's done. So now you have another blue list that's in sorted order. So now we do it again. We go to the gray, pick the next element, and we add it to the blue, and we do the same thing. So we continue to swap, and in this case it continues to swap until it reaches the front. And then here is the first case where now we have blue is in order, we have 1 left in gray that's not in order, so we're going to add the gray. So here you're going to continue to swap until it is greater than the elements on its left. So this is the case where it knows when to stop, is because 6 is greater than 4, and now it's in sorted order. So the basic algorithm is you repeatedly insert an element into a sorted sequence at the front of the array, and you keep swapping until either it's bigger than the element before it or it's at the front of the array or vector. This is what the code looks like. So insertion sort takes in vector passed by reference, obviously, so that it can change. This loop is going to go through each of those gray elements. And then what this loop does is it starts off at the element right behind the first one that you check, and all it does is it compares the two. And so this is that check. If it is greater than all the elements, or if it's greater than the element on its left, then it's done because it's already sorted. Otherwise it's just going to swap them, and that's just going to do all those swaps. And this is a loop that goes down because that's how it's going to go backwards. So insertion sort is interesting in that the best case scenario for insertion sort, and most sorts, but not all of them, is an array that's already sorted. So if you already have a sorted array that's coming in, so V comes in sorted, then insertion sort is going to only take n operations. And the reason that that is possible is due to that break point here. It's very similar to that if statement that I showed you with linear search, the return in the if statement. So what this does is it's doing this comparison, and because you have something that is already in sorted order, every time you do the comparison, it satisfies this condition, and so it's going to break. So this happens 1 time, and this happens n times. So best case scenario is you have O of n. Worst case scenario is that you have to swap them all, right? So so the obvious one would just be if it's in the opposite order that you want it. So let's say you wanted it in ascending order and it was in descending order, then what you would need to do is you'd have to swap every time when you're moving through the list. And so what would happen then is you would have to run this entire loop every time, which is n, and this loop every time, so that would be n squared. And on average, this algorithm performs n squared because oftentimes both of the interior loop is running at least some constant times n, like n over 2 or something. And so we call this algorithm n squared. So what do we really care about? Well, what we care about is that this is a quadratic big O, and what that means is that it grows in proportion to n squared, which is why we call it O of n squared. And so what that means is that if we double the elements in V, it's going to take four times more on average to run that algorithm. So let's think about that a little bit more. It's a little easier to understand with the linear, so this is our first quadratic algorithm. So if we have a vector that has 100 elements, and then we double it to 200 elements, how much longer does it take? Well, because it's an n squared algorithm, if we double the number of elements in the vector, then we get 2n squared instead of n squared, right? And then when you work that out, you get 4n squared, which comes out to 4 times O of n squared. And so that's why it takes 4 times longer. So you can think about it. And yeah, that's it for insertion sort. So insertion sort is an n squared algorithm.